In the last lecture, we talked about how the rate of chemical reactions depends on temperature. And we talked about how the higher the temperature, the faster the reaction is going to go. So how can we quantify that? Well, we can use the Arrhenius equation, which relates the rate constant K to temperature T. The Arrhenius equation states that the rate constant K, so this is the rate constant, that you're familiar with from the beginning of this chapter is equal to some constant A times e to the negative activation energy over RT. All right, so let's define all of the parameters in this equation. Capital letter A is a factor that varies according to the reaction and the reaction conditions, and it's known as the frequency collision factor. Uh, Activation energy, of course, is E sub A, and that's the energy barrier that the reactants must overcome in their journey to products. So we would usually express this activation energy in joules. And the reason for that is that we have the gas constant R in the denominator here, but here we don't want to use the liter atmospheres version of the gas constant. We want to use it in joules per mole Kelvin. So the R that you're going to want to use is in joules per mole Kelvin, and that's why you want your activation energy to be in joules. Finally, the temperature always must be absolute temperature. So you want to put the Kelvin temperature into this equation whenever you're dealing with the Arrhenius. Okay, so that puts it in the form of E. You can also rearrange that equation to get rid of E using natural logs. So here's another version of that equation, the Arrhenius equation, and it's just rearranged in a certain way so that it's in the form of y equals mx plus b, where x is 1 over t, 1 over the temperature, y is the natural log of the rate constant, and the slope m is equal to negative ea over r. The y-intercept is the natural log of the frequency collision factor here. So now we're starting to get to a more useful form of the equation. The problem is, who knows what the frequency collision factor is? So now we want to get a form of the equation where we don't need to know the value of capital A. We don't need to know that frequency collision factor. Now, you can do that if you measure the rate constant, K, at various temperatures. If you measure the rate constant K at various temperatures, you can figure out the activation energy of a reaction without knowing the frequency collision factor by plotting the natural log of K versus 1 over T. Okay, so remember, I have this version of the equation, which is in the form of y equals mx plus b. So in my plot, my y is the natural log of the rate constant. My x is 1 over T, 1 over temperature. And if you measure K at various temperatures and plot the natural log of K versus 1 over T, you get a straight line with a negative slope, okay, because that's in the form of y equals mx plus b. And if you recall from the equation here, that slope is equal to negative EA over R, the negative of the activation energy over R. So the slope of this line unlocks the activation energy. Minus EA over R is going to be the slope of this straight line. Now what you can do is look at 2 points on the line and use their difference to calculate what the slope is. So it would be y2 minus y1. And the useful form of the equation is that the natural log, I'm using the law of logs here to give you a useful version of it. The natural log of K2 over K1, where those are the rate constants at two different temperatures, is equal to the activation energy over R. I got rid of the negative sign here by switching around the t's, the 1 over t's. So you have to make sure that you use the correct form of this equation where K2 is in the numerator and K1 is in the denominator, and then it's 1 over T1 minus 1 over T2. So this is a really useful form of the equation that you can use to do problems and determine what the activation energy is if you don't know what it is. If you do know the activation energy, you can use it to figure out what the rate constant is, for example. So let's do a practice problem using that equation. The following reaction, 2HI decomposes to iodine and hydrogen gas, has an activation energy. Okay, so we know what the activation energy, so has an activation energy of 186 kilojoules per mole. Okay, so here we know the activation energy for this reaction. The rate constant at 555 Kelvin is 3.52 times 10 to the negative 7 liters per mole seconds. So using that information, can we calculate the rate constant at 645 Kelvin? Okay, so again, the rate constant is the rate constant K, little k. So we can use this form of the Arrhenius equation here to solve this problem, because we have the two temperatures, we have the activation energy, we have one rate constant, and we just need to figure out what the other rate constant is. So let's assign the things that we know. I'm going to say that K1 is the one we know. It doesn't matter which you assign to what as long as you're consistent in matching K1 and T1. So K1 is 3.52 times 10 to the minus 7 liters per mole seconds. And T1 is 555 Kelvin, because those go together. I don't know K2, that's what I'm trying to figure out, but T2 is going to be the 645 Kelvin. So I'm trying to figure out K2 there. And the activation energy is given in the problem as 186 kilojoules per mole. But we, of course, are going to need to convert it to joules. All right, so let's look at this equation for a second. Looking at the left side of this equation here, I want to use the law of logs to separate these. Natural log of x over y is going to be equal to natural log of x minus the natural log of y. And the reason I want to do that is because I want to solve for one of the k's. So that's going to be the way to crack open this problem. So I'm going to say natural log of K2 minus natural log of K1 is equal to the activation energy over R times 1 over T1 minus 1 over T2. Okay, so that's what we need to do this equation when we have the one of the k's that we're looking for. So the natural log of K2, that's my unknown, minus the natural log of K1, which is 3.52 times 10 to the negative 7, is going to be equal to the activation energy, which I'm going to convert to joules. So the problem told me it's 186 kilojoules per mole. That's 186,000 joules per mole. And I'm going to put it over my R, which is 8.314 joules per mole Kelvin. Now, in parentheses, I have 1 over T1, which is 555 Kelvin. It's already in Kelvin. If it's not in Kelvin, you need to convert to Kelvin, minus 1 over 645 Kelvin. So everything on the right side can be computed, and then you can add the natural log of 3.52 times 10 to the minus 7. So this should simplify to natural log of K2 is equal to negative 9.24. I suggest you pause and take a minute and make sure that you can do that algebra. Actually, it's more arithmetic. So now, how do we pull the K out from under the natural log? All right, well, if you don't remember how to do that, you need to raise e to the power of both sides. And that is going to cancel out the natural log and the e so that this simplifies to K2 is equal to e raised to the negative 9.24. And you should be able to plug that into your calculator. And that will give you 9.76 times 10 to the negative 5. Now, for the units of K, for the units of K2, let's go back to the units of K1, and we can steal those units, liters per mole seconds. Liters per mole second. So 9.76 times 10 to the minus 5 liters per mole second. All right, so let's think about what happens here and make sure that our answer makes sense. In the problem, we were told that the rate constant at 555 Kelvin is 3.52 times 10 to the minus 7. At the higher temperature, 645 Kelvin, the rate constant went up by almost, 2 orders of magnitude. Okay, you can see it's much faster at the higher temperature. So I hope that makes sense. You can use this Arrhenius equation. Try to use it with a bunch of different problems so you can solve for different variables, not just the rate constant, but the activation energy and the temperature as well.